Alrighty, good morning, everybody. I am Jason Lee with the HPC storage design team at Los Alamos. And today I'll be talking about our project involving hardware accelerated ZFS using computational storage, specifically the hardware stack. So as a bit of review, for those who don't know, Los Alamos is a large multidisciplinary research institution with studying science across all sorts of fields, biology, chemistry, high energy physics, material sciences, a lot of different fields. And in these fields, a lot of simulations are run in order to perform scientific experiments. These experiments are performed using scientific applications, which are not small programs that you can just run on your laptop. These applications run at massive scales, thousands upon thousands of nodes with petabytes of RAM. And they run on our compute nodes as represented on the left-hand side of this diagram. So these applications do not simply run and stop and that's it. They generate tons and tons of data. For example, scientific data used by scientists for analysis or for generating pretty pictures or movies. They also generate data that we call checkpoints, which are effectively save states for simulations so that when they terminate unexpectedly, they can restart at a point near where they terminated instead of being forced to restart at the very beginning. And all of this data is does not comprise of a handful of bytes. It's not just a couple of files, a couple of gigabytes each. Some of these files can be several terabytes in each. Yeah. Sorry, I got distracted one moment. Right. Right, so all of this data is destined for the Lustre file system, but because the Lustre file system is backed by hard drives, we can't write directly to Lustre. There's simply not enough bandwidth for the scientific applications to do so. If they tried to write directly to the Lustre hard drives, I.O. would suddenly become the bottleneck of these simulations, which is not what scientists want. They want to do science, not I.O. So instead of writing to Lustre, they instead write to the burst buffers, as shown towards the middle leftish with the orange boxes. This burst buffer is effectively scratch space consisting of a handful of petabytes of flash, which are able to ingest the data at high enough rates so that I.O. does not become a bottleneck. So these burst buffers, once the I.O. is completed, the scientific applications are able to continue doing their science while the data is streamed out to the hard drives at a slower rate, without blocking the scientific applications. So these burst buffers have served us well. They are used in Trinity and a number of other systems, but they are a additional layer of storage which introduces complexity. So to that end, for our next generation parallel file systems, we plan on removing the burst buffer layer and writing directly to Lustre. However, as I mentioned earlier, we can't write directly to Lustre backed by hard drive, so instead we will be writing to Lustre backed by NVMe SSDs. Another change that will be made in our next generation of parallel file systems is that these backing NVMe SSDs will not be dedicated to the Lustre file systems. and will instead be a resource from which many different services can pull from. Additionally, due to the economics of Flash, we probably will not be building a system that with the same capacity as our hard drive layer that we currently have, and the capacity will be lowered to about 10 to 50 petabytes. Despite this lowering of capacity, we will still be writing the same amount of data or more to storage, meaning that we will have to use our storage more efficiently. To do that, we will be compressing our data. So we will, of course, still have hard drives and other mediums such as tape in our colder storage tiers, but those are outside the scope of this presentation, and I mentioned them for completeness. So in both our current generation of parallel file systems and our next generation, we will be writing to Lustre. Lustre is a parallel file system that is backed by an underlying file system, and one of those file systems is ZFS, a open source file system that is actively being developed and has a good sized community. It provides high data integrity through erasure coding, mirroring, snapshotting, and checksumming, and has many built-in features such as encryption, deduplication, and compression. In addition, it is a file manager, a volume manager, so administrators don't have to use another package such as MDADM to merge their physical devices into a single virtual device. So to illustrate how flexible and powerful ZFS is, let's say we had 8 storage devices, say hard drives. We can organize them in many different ways, such as 4 sets of two-way mirrors or 2 sets of 4 drives with erasure coding enabled. In this particular case, we have erasure coding with 2 data drives and 2 parity drives, which is known as RAID Z2 in ZFS. You might know that configuration better as RAID 6. So ZFS has traditionally been used with hard drives and has many design features that make ZFS with hard drives or backed with hard drives very efficient. However, for our next generation of parallel file systems, we will not be using hard drives. We will be using SSDs. So the first thing we did was place a few SSDs underneath our ZFS pools, otherwise known as Z pools. So here we have a graph showing performance benchmarks that we obtained with our performance benchmark tool. The black dotted line at the top shows the performance that we obtained by writing to the raw devices, which there were 10. The red line shows the performance we obtained with a Z pool consisting of 10 data drives of 2 parity drives. As you can see, these lines are nowhere close to each other. In fact, we dropped about half of the available bandwidth just on the floor unused, which is a massive waste of bandwidth. So this is due to several memory copies that are found inside ZFS, and we have a project that has occurred in parallel with this project that will solve this issue. So for the purposes of this presentation, the red line is the maximum performance achievable. So now let's zoom in onto that red line. In this graph, just as before, we have the red line with our representing the maximum performance achieved by a erasure-coded Z pool, which is at around 11 gigs a second or so. So the plan at Los Alamos is to use multiple features of that are provided by ZFS, such as checksumming and compression. So the first thing we did was add checksumming to our performance benchmarks. And as you can see in this graph, the line is basically the same as the red line. We suffered a performance loss of less than 1%, which is great. We added a full-blown function and basically didn't lose any performance. The next operation we added was compression, which, as I mentioned before, we will need since our next generation parallel file system capacity will be reduced by quite a bit. And the algorithm we chose to use as our baseline was LZ4, an algorithm known to be pretty fast at cost of lower compression ratios. And with LZ4 enabled in our Z pool, we suffered a 17% performance loss, which is not too bad. Could be better, but we also didn't lose too much. However, as it turns out, LZ4 does not compress scientific data particularly well. Our data consists of very dense floating point numbers, which is known to not compress well, and we needed a better algorithm. And the algorithm that we need to use is gzip. So we enabled gzip in our Z pool and ran our performance benchmark on it. And instead of losing just some more performance, our performance actually dropped by a total 94%. Down to that blue line at the bottom. That blue line is around 600 or 700 megabytes a second, which is crazy. We simply can't deploy a file system with that bandwidth. You might be thinking, what about, you can throw more CPUs at it. Unfortunately, we cannot. The x-axis on this graph shows what happens when we throw more IO threads into the writes that were occurring and as you can see, despite having hundreds upon hundreds of threads, the performance flatlined and stayed flat. The other issue is that each of these operations scans memory at least once, if not more, and with the number of steps or operations involved and the sheer number of threads being run, memory bandwidth was simply being consumed completely, resulting in this reduced performance. Yes? So for both of these lines, we used data buffers that compressed 1.3 to 1. The idea was that even though we used different data buffers, the same amount of work was done for each of these lines. So if we were to run the LZ4 data buffer through gzip, we would actually result in a higher compression ratio because gzip compresses that much better.
So the final compression ratio is 1.3 to 1?
Yes.
Combined both?
No, each of them.
Each of them. So similar compression ratio?
Yeah.
For the test.
For the test. Yes. But it represents our actual data. So the pathway we chose to go down to solve our issues was using computational storage to offload operations that are known to be CPU and memory bandwidth intensive. Computational storage, as you know, can be implemented with FPGAs, such as Idetacom's no-load computational storage processor, or full-blown DPUs, such as the Bluefield 2 by NVIDIA. So you might be wondering to yourself, why doesn't ZFS already support offloading with Intel Quick Assist? Yes. However, Intel Quick Assists or QATs don't exactly work on my AMD machines. Additionally, in order to enable the Intel QAT in ZFS, you have to reconfigure ZFS, which, as I've been informed, is unacceptable in certain situations. Additionally, each offload operation with the QAT is done independently of each other. So for example, if you have the 3 operations, encryption, compression, and checksumming chained one after the other, data would start off in memory, be mapped onto the QAT, and be encrypted, and the ciphertext would be mapped back into memory. The ciphertext would then be mapped back onto the QAT, compressed, and the compressed data would be mapped back into memory, only to be mapped back to the QAT again for checksumming. That is a lot of memory traffic that we found to be unnecessary. Yes?
Which version of CPU or maybe QAT version used in this?
Oh, we never tested the QAT. It's just.
Yeah, because the QAT can support chained output, so I.
Oh, it does. Oh, well, darn. All right. Well, the QAT code in ZFS is also not particularly extensible. It sort of calls the QAT API directly. So if the API were to change at some point, or if a user wanted to use a different accelerator, it would not be easy to do so. You would have to make a full series of changes and have them approved, or open a pull request, have the modifications approved by the ZFS community, reviewed and approved by the community, and then finally merged into the main line, which can take quite some time, and during which you'll be running a custom version of ZFS, which may not be acceptable. So our solution was the accelerated box of flash and the ZFS interface for accelerators, a co-designed hardware and software solution. So on the right side of this diagram, you'll see a box labeled the accelerated NVMe enclosure. This is an enclosure filled with SSDs and accelerators with possibly even a DPU such as the Bluefield 2. And all of this is exposed through NVMe over Fabric and used by a host system that owns the Z pool via a series of changes we made in ZFS, which communicates with a small software stack consisting of the DPU-SM and a provider, which I'll get into later. So in addition to communicating with, or using accelerated storage in a remote location, our software stack can be used in with locally attached storage. So just as before, we have ZFS on the left-hand side, and data comes into it. The data is passed off into our modifications, the DPU-SM, and the provider. This software stack will then communicate over the PCIe bus to direct attach NVMEs and or computational storage processors or devices. We have tested both of these configurations, and it works just fine. So as I said earlier, this presentation will focus on the software side of this project. Yesterday, there was a presentation about the hardware. Hopefully you didn't miss that. So for this project, we focused entirely on the write portion of I/O. So to give a quick overview of how ZFS works with writes, here's a diagram just showing a super high level of what happens when your program or when a write call is performed. The data is passed into the ZFS POSIX layer at the top, which is then passed into the data management unit layer, which then forwards the data and the command into the adaptive replacement cache, the ARC, in the middle. So instead of passing this data further down into the Z.I.A pipeline, the data is actually copied into the ARC, and the write command returns saying that the write has been completed. While this data sits in the ARC, more data comes in, and eventually watermarks are passed, and the data is flushed out into the ARC for transformations and aggregations, and eventually landing in the backing storage. So what we did with our modifications was modify the Z.I.A pipeline and shunt data out of ZFS into the DPU-SM, into a layer called the DPU-SM, which then sends the data into a provider, which communicates with the accelerator, which does the actual operations, including I/O. So I'm going to go slightly out of order here and start with the DPU-SM, whose full name is the Data Processing Unit Services Module. It is a simple kernel module whose main purpose is to provide standardized APIs for leveraging computational storage. The two APIs are the provider API, which faces accelerators, and the user API, which is what users will call no matter what accelerator they use. The DPU-SM also acts as a simple registry for providers to do some basic bookkeeping and quick checks that are generic enough that it can do. Next, we go to providers, which are also kernel modules. We expect these to be implemented by accelerator vendors since they know their API best. Sometimes they wish to keep their API private or secret. Whatever the case, we generally expect vendors to implement them. A provider is effectively a translation layer between the accelerator's custom API and the DPU-SM's API. And providers simply declare generic functions such as compression or checksumming. However, in order to providers also declare what the accelerators provide. So in addition to the generic functions, it will also provide the DPU-SM and the provider flags saying what specific algorithms are provided. For example, for compression, it may be this accelerator only implements gzip, not LC4, or maybe some compression or checksum algorithm, but not another one. Implementing a provider should be pretty easy, especially for a vendor. All you have to do is include your accelerator's API or header, and then include the DPU-SM's provider API. With those two headers, you should be able to fill in the DPU-SM provider function structure, which is a series of function pointers that you can view as analogous to the Linux ZFS function pointer structure. And once you have those functions defined, you can register your provider with the DPU-SM on kernel module init. The main goals of a provider are to be able to create handles that you give to the user that reference accelerator memory. With that handle, you want to be able to move data from memory to the accelerator via some mechanism, whether it's copying or DMA or something else. Once user data has been placed on the accelerator, the handles should be able to be used for operations such as compression or checksumming or anything else your accelerator provides. One important thing to note is that communication with the accelerator is connection protocol agnostic. So for instance, in our ABOF flash enclosure implementation, we use an NVMe over fabrics. However, or because that is the latest and greatest communication protocol. If tomorrow somebody came up with a brand new protocol, you are perfectly welcome to implement a new provider using that communication protocol. Yes?
Are your providers designed to be stackable so that if you have a couple of different vendors providing useful services, could you stack them in some way?
You can provide. So his question was, are providers stackable? So it is possible to register multiple providers with the DPU-SM and have them all going at the same time. And then you would have to modify your user to be able to use all of those providers at once. But in our case, we only had one hardware accelerator with one provider, so we did not. But in theory, we should be able to. So using a provider is also pretty simple. All you have to do is include the DPU-SM's user API, and with it you can find the provider that you want, and then use the the provider's functions that are wrapped by the DPU-SM. And just as a provider does a handful of things, users will do the mirror image of those things. So first, a user should get handles to the accelerator memory from the provider, move data from memory to the accelerator, and then finally use that handle, which contains their data, to perform operations such as compression or checksumming. So now finally we get to our user, which is ZFS. So we modified the ZFS Write Pipeline with a series of changes to call into the DPU-SM, which the set of changes was called the ZFS Interface for Accelerators, or Z.I.A. These changes allow for transparent acceleration of ZFS write operations, meaning that users should not have to modify their code in any way to write data or read data afterwards. Their simulations do not have to change, their scripts don't have to change, their analysis code does not have to change. If anything, the only changes they should notice is that their write operations happen faster.
So you have full operation with accelerators from compression to I/O.
Yes.
So can you tell me in which accelerator it was carried out processed? You have to accelerate to running DPU according to your illustration.
Yes.
Running DPU and the other in year to SSD.
Right.
So which was the process of which accelerator?
So our enclosure included was a Bluefield 2 with an attached Idetacom no load on a PCIe bus. Yes. Does that answer?
And compression was processed in DPU or?
It was processed on the no load.
What about checksum and rate?
I believe those were in software. Maybe the erasure coding might have been in hardware. There were some weird settings with our no load. All right, so although users shouldn't really detect any changes with their usage of ZFS, administrators will. So currently we need to reconfigure ZFS with a flag to tell it where the DPU-SM is. As I mentioned earlier, reconfiguring ZFS might not be acceptable in certain situations. So we expect that when Z.I.A. is merged into ZFS, Z.I.A. will simply always be compiled in. That will not cause issues because we have written the code in such a way that if Z.I.A. does not find the DPU-SM at load time, it just simply errors out and falls back to using the ZFS software code. So, yes.
So on your previous diagram, you showed original path from the Z.I.O. pipeline down to the VDEVs.
Yes.
And that path is preserved for that backward compatibility. Is it used during production for anything else?
What do you mean, is it used for anything else?
Well, so if your DPU-SM is there and everything is working normally and you've got everything configured correctly, the I/O shunts from the Z.I.O. pipeline through Z.I.A. down through your special stack of circles there,
yes,
and straight out to the devices.
Yes.
So there's a line between Z.I.O. pipeline and VDEVs.
Yes.
Is that used for anything?
Yes, for error handling. So I will get to that in a moment. All right, so let's see, where was I? So once a administrator has reconfigured their ZFS, rebuilt it, and created a new Z pool, all they have to do to start up the offloading process is to call Z pool set Z.I.A. provider equals whatever the provider name is, and then enable offloading for the operations they want. For example, compression. They can simply run, or for compression, they can simply run Z pool set Z.I.A. compress equals on. So note that this only has any effect if the ZFS operation itself is offloaded or is enabled. So for example, you might have enabled compression offloading, but the compression stage itself wasn't turned on. If that's the case, the offloading doesn't do anything since you're not compressing. So the ZFS Write pipeline looks something like this. data comes in from the ARC and is passed into the ZIO stage with ZIO pipeline, which is consisted of multiple stages. The stages we will be using are compression, checksumming, erasure coding, and issuing I/O to the backing devices. So in order to not be too repetitive, here's a general description of the changes that were made at each stage. So each of compression, checksumming, RAID Z, I/O. So at the start of a stage, if ZIA detects that the data was not offloaded, the first thing that happens is the data is offloaded. Then the operation is run, so the data could be compressed or checksummed. And then a status code is returned. So normally this should simply be a success status code, and which is just a very small value, say an integer. However, note that the data itself is not returned and instead remains on the accelerator. So normally the data in fact never returns to the accelerator, and however, if ZIA were to fail for whatever reason, the data is brought back into memory, and the same operation is run in software instead of returning an I/O error. On the off chance that somebody took a proverbial backhoe to your accelerator and data cannot be returned to your to memory, it is still possible to restart the entire write pipeline from the beginning because a copy of the original data is still available inside ZFS. However, we haven't gotten to implementing this yet, so watch out for that. So this is what the ZFS Write Pipeline looks like with ZIA enabled. So as before, we have compression, checksumming, erasure coding, and I/O, and the I/O stages. When the data hits the first stage, the compression stage, ZIA will notice that the data is in memory and has not been offloaded. So it offloads the data onto the accelerator and then runs compression on it. A simple OK code is returned back to the host, but the data stays on the accelerator. Then when ZFS reaches the checksum stage, it will once again check whether or not the data is in memory, because it is the second stage, it will notice that the data has already been offloaded. So it will run checksumming on the data that is already on the accelerator. And the same will happen with the erasure coding and the I/O issue stage, meaning the data is issued out from the accelerator, not from the host. So here is a graph showing, that we have seen before with Z pools with different configurations. And however, this graph has an additional line. So previously, our focus was the blue line at the very bottom with erasure coding, checksumming, and gzip enabled in our Z pool. And the performance of our software ZFS was rather poor. By offloading data to the Idetacom no-load accelerator, we were able to achieve a 16x speedup with, as shown by that black line on this graph. So notice that not only is this line above the software gzip line, this line is also above the software LZ4 line, meaning that not only are we compressing data faster, we're compressing data faster and better than what can be achieved in LZ4, meaning that we are using our storage systems far more efficiently than was achievable through software. So in addition to offloading the ZFS Write Pipeline, we also offloaded ZFS Resilvering, which is the operation that is performed to restore data to an erasure-coded Z pool after a disk failure. So resilvering consists of 3 stages: I/O start, I/O done, and issue I/O. So I/O start is the stage where data is read in from the backing storage into memory in preparation for the actual resilvering. On the other side of this graph, we have the issue I/O stage, which is the same issue I/O stage as the one found in the ZFS Write Pipeline. So we simply reuse that code. The core of Resilvering can be found inside the IO done stage, where missing data is reconstructed, checksums are verified, and parity columns are verified. So just as before with the ZFS Write Pipeline, we mirrored the operations in Z.I.A. So when data comes into the IO done stage, it is first offloaded and then has missing data reconstructed, checksummed, and parity columns verified. So note that data is only ever offloaded one time at the very beginning, despite the number of sub-stages within this stage, or sub-functions in this stage. This was to prevent weird thrashing if, for whatever reason, you had errors in alternating stages. So we wanted to avoid that. So if an error were to occur, the data is brought back into memory, and the remainder of the resilver stages are performed in memory and issued out through the host instead of through the accelerator. So at the moment, I do not have numbers for Resilver. We are still working with our vendor to implement some features that we require. So sorry about that. So I guess in conclusion, we have implemented a full-blown, we have offloaded an existing file system with computational storage. For more information, you can find the Z.I.A. code changes on GitHub in the ZFS repository in a pull request. The data processing unit services module can be found in a GitHub repository in the HPC organization. And earlier I mentioned that there is a project that occurred in parallel that aims to fix the performance gap when using NVMe SSDs underneath Z-pools. That code can also be found in a pull request in the ZFS repository.
That one's to eliminate memory copies, the gratuitous memory copies.
Yeah, yes. Well, thank you, everybody. That's all I had.